And others will lead, and then Osama will finish our workshop for this week. So please, Johannes.
Thank you, Haley, for the introduction. And I also want to thank all the organizers for giving me this opportunity to speak here today about degrees of freedom of the marginal ice zones wave ice system. Now, in the past workshop and also in the present workshop, we've heard a lot about why it's important to model the marginal ice zone and why we need to understand wave ice interaction. And I'm not going to repeat all this. Instead, I jump right into it, namely, how do we model this? And the first thing we have to think about if we want to model any physical system is what are the relevant degrees of freedom which we should use to formulate our model. So the marginal ice zone is really complicated, right? So we heard from Luke that there are waves washing over the ice. We know that waves can break the ice up, which is a very important process because it influences the flow size distribution, which is again important for all kinds of other things in modeling. And the flows can raft on top of each other and change their internal structure, all kinds of things which are really complicated by themselves. So how can we model all this on a large scale at all? So I thought maybe before we go to the marginal ice zone, we think about some physical system which is much more simple. Let's say a rock. Okay, so in principle, a rock consists of lots of quarks and electrons, which all have their degrees of freedom, and there are lots of them in such a rock. And it would be both extremely complicated and completely useless to model a rock in terms of electrons and quarks. But luckily enough, nature is kind, and at low energies, all these degrees of freedom lump together, and they kind of freeze out. So we can describe a rock in terms of its momentum, angular momentum, and all these things, right? But if we increase the energy of the system, the rock will melt, and now we have to think about degrees of freedom to describe a fluid. And at even higher energy, we talk about a plasma, and we have to take into account an electromagnetic field. So what does this have to do with the marginal ice zone? The point I want to make is that it is not so obvious in the marginal ice zone what are actually the degrees of freedom we want to talk about. And even if we decide upon one particular description, we have to be aware that once the energy scale changes, for example, we go from a calm sea state to a rough sea state, the relevant degrees of freedom may change as well, and our models will deteriorate in their predictive power. So let's stick to the calm sea states. What are the degrees of freedom? So this question has many answers, or proposed answers, and in my PhD thesis, which I'm hoping to finish soon, I'm looking at 3 different proposals. One are effective media, the transport equation, and flow models. So in this talk, I'm going to talk about all 3 of these proposals to classify the marginal ice zone. And let's start with the effective media. So the idea of effective media is that on large scales, the specifics of the fine structure, they somehow average out, and the waves only see some effective medium. We already got a very nice and extensive talk from Haley about one of these effective medium models. So I'm going to keep this section very, very brief. Other people have worked on several kinds of things which one could call effective medium models, but I'm going to talk actually about Haley's model and some work we've done 2 years ago in this article. So the idea of the Wang and Chen model was to describe all the near surface processes in the ocean by a viscoelastic fluid layer. So I call it the ice layer here, which is on top of a inviscid water layer. But it is not representing a sheet of sea ice, but everything that happens at this ocean surface. So it's a mixture of ice floes and fresh ice and phrasal ice and whatever we have there. But on large scale, one may argue this behaves as some effective material, and there are arguments for this to be a viscoelastic fluid. Now, viscoelastic fluid means you have two essential parameters, an effective shear modulus and an effective viscosity in there. But unfortunately, this model is quite complicated. So we simplified it to and used just a viscoelastic thin plate and interpret the parameters also as effective parameters. And we found that many of the interesting solutions are actually resembled by this simpler model. But both models work in the same way. You have equations of motions and boundary conditions, and you make a plane wave ansatz, and you get a dispersion relation from that. And the dispersion relation requires a couple of parameters, like the shear modulus and viscosity. And you put them in there, and you get complex wave numbers, which contain the real part, which has the wavelength in it, and the imaginary part, which is the attenuation rate of the wave, which is what we are really interested in. So both models work in the same way, and they predict similar things. I just want to compare the dispersion relations for a moment. So this is the thin plate, and this is the viscoelastic fluid dispersion relation. And one advantage of the thin plate model is that the inverse problem is simply solved, whereas for the viscoelastic fluid model, it's not so easy to do. So if you want to read more about this, check out our article. I want to skip to the next topic. The only thing I want to mention here is the main difficulty I see with both of these models, this class of models, is that you need to calibrate them with the very data they are supposed to predict. However, the best solution to that I've seen so far is what Christian Samson presented in the previous workshop. So that's what I think where these kinds of model will go in a way, because he uses a homogenization method where you can look at ice flow, size distribution, and shape distribution, and derive these parameters from satellite observation, basically. So the other kind of model I want to talk about is uses different degrees of freedom. Right? We had the viscoelastic fluid layer as one way of describing ice. Another way of describing the marginal ice zone and the wave-ice interaction is via transport equations. And there the idea is that you actually just have a single scalar field called the wave intensity, which captures all the things, which is the main degree of freedom in the marginal ice zone. And we want to model everything in terms of the scalar field, which is defined over the entire horizontal ocean domain. So this is actually how WaveWatch 3 and also the waves and ice model Tim was presenting recently works. You have the scalar field here, and it is advected with this advection term at some group velocity, and then you have source terms which reflect the different processes which influence this propagation. And one source term is the ice source term here, but it is not very clear how the source term should really look like. We think it's this kind of form. So there's some attenuation from the processes in the ice, and some scattering, so redistribution of the direction in which the waves are propagating. But what alpha and the kernel here are is user-defined in the WaveWatch model. And I was wondering, how do we connect that large-scale description to the local description we usually use, where we say, okay, ice flows are basically thin elastic plates, and we can write down a boundary condition and consider ice flows and propagation of waves. And then we use the linear potential flow theory as usual with a velocity potential phi on local scales, right? If you want to model individual ice flows. So the question is, how is this kind of model related to that kind of model? Now, everything that follows now is more of a mathematical exercise and an interesting procedure. I'm not claiming that what I do will be of physical meaning in the end. It's just mainly to point out how complicated it can be to actually understand this connection. So what I thought is, okay, I tried different things, and one thing I tried was, which kind of worked, was to consider a homogeneous ice cover, but its thickness is perturbed somehow. So, and the procedure I'm going to go through now is, I do the things twice. First, I consider a constant ice cover, constant thickness. I use a multiscale expansion to get to a Schrödinger equation for an amplitude envelope. And then I use a Wigner transform to get a Boltzmann equation for that. And the Boltzmann equation is this thing which looks like what we use in the wave-watch model. But this Boltzmann equation doesn't have a scattering term in it. That comes from a random ice cover where I can go through the same procedure and recover the scattering term in the end. So let's start here with a multiscale expansion. If you're not familiar with multiscale expansion, it may seem a bit odd. You use several variables to describe the same dimension in your model. Right? So there are several time scales and several spatial scales for the same direction in space and the same direction in time. But that is a often used technique. So we now express our velocity potential in terms of all these variables and make an ansatz where we say, okay, we have a plane wave which is modulated on large scales in its amplitude. And well, we can plug this ansatz into our Laplace equation for the fluid domain and get a couple of equations. And we can do the same for the boundary condition between the water and the ice or elastic plate, and do the same thing there, and we get another series of equations. And then we can go on solving these things, starting from the lowest order, writing down a general solution, which gives us a dispersion relation from the boundary condition here, and then going to next order, where the general solution contains the amplitude envelope of the previous solution, but that now has to satisfy a solvability condition, and that is the thing we are interested in because it's a condition, an equation in the amplitude envelope. And so the first order condition just moves the amplitude envelope, and it keeps its shape and just moves in the x direction with the group velocity actually. And then you do the same on second order, same process, and you end up with this equation. And then you collect those two equations together and say, okay, these are actually expansions in a Schrödinger equation. So this process is well known for just water waves. I just did the same thing with ice on top. Okay? So we get a Schrödinger equation here. And I thought, so when I read about this for just water waves, I thought, well, I know how to get a Boltzmann equation from a Schrödinger equation. So let's just do that. And that works via a Wigner transform, which is the following. So here's our Schrödinger equation again. And then I define a Wigner transform, which is this thing here. It has a long, interesting history. You may look this up in Wikipedia. The important thing about this is if we integrate over all wave numbers, we get amplitude squared. So the Wigner transform is something we could think of as a wave number resolved energy density. And then you can use the Schrödinger equation to get an equation for this Wigner transform thing. And that is actually the left-hand side of the Boltzmann equation. So we see this transport term and some new dispersion term which comes from the second order part of the expansion. and that refers to the left-hand side of the thing, as I associate that with the left-hand side of what we have in WaveWatch. Only that we have this extra term here. So the question is, how do we get this SI's term? So for that we use the random ice cover, random thickness perturbation on the ice cover. So instead of this situation, we look at that situation. And I played around with this and tried many different things, but the only thing that seems to kind of work is having a thickness perturbation which is small compared to the mean thickness, and it should depend on the local or fast scale. Now, okay, we can do that and repeat everything we did before. We get the expansion for the Laplace equation, it's the same thing as before. We get some new terms in our boundary condition from the thickness perturbation, as we would expect. And, well, then we end up with solvability conditions, which now get these new terms, these new potential terms, V1 and V2 here, which is exactly what I wanted to have, because they end up being the scattering terms in the Boltzmann equation. But we also get these delta nu and delta CG terms, which I don't like. So what do you do with that? You could say, okay, it corresponds to this kind of Schrödinger equation with those annoying terms in there. And I was stuck. And the only way to get forward was if I could find some reason to ignore these terms. And so I just plugged in numbers. Everything is non-dimensional here. And I find that this delta nu is several orders of magnitude smaller than 1, and delta CG is several orders of magnitude smaller than CG. But of course, you have the epsilon there. So everything which follows now is very hand-waving, and I cannot say for sure that what I do really works out after that. But since these terms are small compared to the corresponding terms, I hope they don't matter. So I just throw them away for now, and I look at the bigger problem later. Because then I get only this potential term here, which contains the thickness perturbation. And I have a Schrödinger equation with a scattering potential now, which has exactly the order I need there. Because now if I express all of this on the large scale again, because I'm looking at the large scale for the Boltzmann equation, and then use the Wigner transform. Slightly differently defined with an epsilon square in here because you are working on the large scale. You get, again, the Boltzmann equation left-hand side, but now this extra term here, which is fairly complicated, but you can apply a few math things there and end up expand the Wigner transform as well in epsilon, and then compare orders and so on, and you end up actually with a Boltzmann equation, where every term is now defined in terms of the thickness perturbation correlation length and the mean thickness and the ice properties and so on. So again, we have these 4 terms, and I think they somehow correspond to those terms in WaveWatch, except that I made this simplification in the middle. Which is not really justified. I just want to get somewhere, you know. So my point is not, well, first of all, I can evaluate all these things now, just plug in numbers, solve integrals, and everything is analytic. So I get a picture of how attenuation relates to wavelength, for example. Don't take that with too much seriousness, because, as I said, I made this approximation, and also, so I made too many assumptions for this to be physically observable in any way, I think. However, the point I really want to make is that it is not completely obvious how the sea ice term should look like in the Boltzmann equation. Right, you can do lots of computations, you can have different arguments, but there is no clear derivation of this term must look this way and no other way. That's the term I want, the statement I want to make, basically. All right, so that brings me to the third part of my talk, which is about flow models. Yet another way of choosing degrees of freedom in the marginal ice zone. And here we say we are talking about individual ice flows. That immediately gives us the problem that we have lots of degrees of freedom here. So lots of ice flows which may scatter and interact. But it's also the most realistic description, I would say, because we actually have ice flows in the marginal ice zone, right? So lots of work has been done in this field. Fabian, for example, my co-supervisor, has a code for scattering of ice flows where you can put in lots of ice flows and it all works nicely. But I went a kind of different direction. So remember this slide again. For flow models, we usually assume that ice is again a thin elastic plate. So we have those boundary conditions and the condition in the water and the boundary condition at the seafloor, and we get these equations, and then we want to solve a scattering problem. So what happens in the horizontal direction if you have just a piece of ice on the water? So in scattering, well, you will know that you have an incoming wave and an outgoing wave and a transmission coefficient which tells you how much the wave gets through and how much is reflected. But now what happens if we are uncertain about parameters of that model? And this is something that may interest you generally, because the things I describe now can be applied to any kind of model. And I've developed a Mathematica package to make it easy to work with this kind of method. I'm going to present this package in the end. Here is just a simple way of using it, these methods, for a linear scattering problem, but it should work for non-linear scattering problems and also in 3 dimensions. Same technique. So let's say we have a flow and we don't know its length exactly. We say, okay, length is some L0 plus alpha L1, and alpha is a random variable for which we only know the distribution. Now, for example, the flow size distribution, right? So what we do then, so we have an input distribution, here a uniform distribution. Then we look in the linear problem, the reflection coefficient depends on the flow length in a pretty simple way. But this transforms this input distribution of our random length into an output distribution which looks like this, with some mean and some variance here. And we want to compute this mean and this variance as efficiently as possible. So, and this of course will change if you choose another distribution. Right? If your input parameter is distributed differently, you get a different output and different variance of your output. So the framework I work with is called generalized polynomial chaos. And it sounds more complicated than it actually is. The idea is, so let's say we want to compute the reflection coefficient. Then we expand the reflection coefficient in terms of some polynomial basis. And this polynomial basis is a special kind of basis because it is adapted to the probability distribution we assign to our random variable. Specifically, the scalar product with respect to which this polynomial basis is orthogonal to has a weighting function which is just the probability density function of our distribution. And one can show that this sum converges best if you use this basis as compared to any other polynomial basis. Now, okay, you can solve, you use the scalar product to get the coefficients in terms of an integral, and you can solve that integral with Gauss quadrature, for example, but not for the usual Hermite polynomials, but for whatever polynomial basis you use here. Yeah. And then you see that the expectation value is just the 0th order coefficient, and the variance is the sum of the squares of the other coefficients, which is very practical. You can also compute higher order moments, or if you are looking at complex variables, you can come up with different rules, or you need a few more numerical, or another numerical computation actually. The important point is that you avoid evaluation of your model. So here's a comparison. Expectation of the transmission coefficient, but I could have written variance or reflection coefficient, whatever. They all look the same. The green points are corresponding to the error of the collocation method I just described. So that error decreases exponentially, and to some constant where the machine error adds up. Here a bit higher than with the other method I cannot talk about because I don't have the time, but it's another class of generalized polynomial chaos methods, which is harder to implement though. So and this up here, this is quasi Monte Carlo, which would be the easiest to implement, but you see it does not converge very fast. So here's one interesting result I derived with that. Since evaluation is now relatively quickly, I can evaluate the expectation or variance of our transmission coefficient or reflection coefficient many thousand times for different flow thicknesses and different frequencies. What you see in the background is the reflection coefficient for a fixed flow, and overlaid to that you see these dashed lines indicating the contours of the expected reflection coefficient. And the interesting thing is that this expected reflection coefficient changes a lot depending on what distribution you use. So this is for a uniform distribution, this is for a beta distribution, and you can do other things, you put in other distributions and get other results. So the point I want to make with this picture, or these two pictures, is that it is maybe dangerous to assume uniform flow size distribution, which is practical for some theoretical work, but expectation values of their transmission vary a lot depending on what distribution you really assume. So I guess we can get to the fun part. How many of you use Mathematica, or have ever used Mathematica? Okay, a few. That's good. Good. So, hey. Hello. Good. Okay, so I'm showing you now the Mathematica package which I've developed. Is the font, come on, is the font size large enough in the back rows? Okay, good. Is it? Yeah, good. All right. So for those who have not used Mathematica before, I give a very quick introduction. The idea of Mathematica is that everything is an expression, and something like 7 power 172, for example, is an expression, and you hit Shift Enter, and this expression is sent to a program in the background called the kernel, and the kernel applies rules to that expression until it doesn't change anymore, basically, and it sends you the resulting expression back, which is a large number, obviously. And you can send all kinds of expressions, like an integral, and it solves you this integral then analytically, or ask random questions like, tell me, hey.
Nope.
Okay, tell me where there are known shipwrecks in the Atlantic Ocean, and it gives you a map of shipwrecks in the Atlantic Ocean. So it's quite a powerful system, in contrast to this projector. But now, yeah. Okay. So now let's load my package, and this defines a couple of new commands or expressions, and I'm only going to talk about two of them because the others are also interesting, but I don't have infinite time. So first one is GPC basis. I just told you about the generalized polynomial chaos basis, which is the basis which is a polynomial basis which is orthogonal with respect to the scalar product defined from the probability density function of your distribution of your random variable. And you can construct this thing with this GPC basis code. Is it still large enough? Yeah? Good. So here you say, okay, I have one random variable called x, and it should follow a normal distribution. And I want the first four terms of this basis, and it gives you the first four terms of this basis. Also gives you analytic expressions if they are known for some known distributions. And this works in any dimension with most distributions. So you can say I have several random variables, x normal distributed, y gamma distributed, and z uniform distributed. And it tells you also a basis for this kind, also with exact numbers. It took a bit longer now because I didn't tell it how the basis looks like for the gamma distribution. It has to construct the orthogonal basis by itself. So there are lots of distributions already available from Mathematica. Here's a list of those. There are more than that. Yeah, a list of those. But of course, you may want to define your own distribution. So let's take something which is gamma distributed and pretend we don't know it, and construct a probability distribution with a density function which looks like this. So piecewise function. But it still works. I say GPC basis. GPC basis of this distribution, which I just defined here, with a few extra options to make it faster, and evaluate that, and that gives me the basis. And then I can check the orthonormality, and it's actually orthonormal. So if we integrate any two of these polynomials together with the probability density function, we get Dirac delta. So now comes the interesting part, the collocation method. So this implements basically everything I've just presented in the last part of my slide presentation. So here is a model, let's say x cubed, and that contains a random variable x, which is uniformly distributed here. And this collocation procedure now computes expectation and variance in a way that the model is evaluated the least number of times possible. Okay, that is the point of it. So the thing which is returned is called a collocation data object, which contains all kinds of things, especially the variance of this model output. Now, obviously, x cubed is a very simple model. We can do multiple random variables with different distributions, like x power y with different distributions here, half normal and beta. But we can also do something more fun. Consider a double pendulum as a nonlinear system. I guess everybody has encountered this before somewhere. described by these equations, and we can solve them using ND-solve here numerically. Takes a moment, and there we are. And then we get a solution which looks like this if we animate it. So we are looking at this double pendulum, and the thing I want to try now is say, okay, at the initial position, we want to be uncertain about this middle joint's vertical velocity. And we want to compute the x-coordinate of the outer part here after 4 seconds. So since this is a chaotic system, we'll get a chaotic answer after a certain amount of time. So I implement this as my model, which depends on the y vertical velocity of this middle joint, and returns the x2 coordinate after 4 seconds. And I can evaluate that lots of times to give you an overview, but that takes a long time, so I did this beforehand and saved the result. So you can look at it right now. So as the initial velocity changes, the final exposition is first rather smooth, but then it clearly gets chaotic there, right? Now, this model takes a while to evaluate, so we want to estimate the variance of this thing and the expectation value without evaluating the model too often, right? And that's what my collocation code does. You put in this model, and you say, come on, you say alpha is uniformly distributed, and here we have, we say it can evaluate 13 times and give me the best approximation you can get from that. And then it computes a moment and evaluates the model 13 times. And then, we get this thing. So the collocation data object also contains the polynomial interpolation which it uses in the end, and that looks like I think it's coming, right? Yeah, it looks like this. So considering that we had only 13 times in such a chaotic system to evaluate, it's actually not bad, right? And it gives us this expectation value indicated by the solid line and the standard deviation according to those dashed lines there. And we can see how this changes with a different distribution, say a transformed beta distribution which looks like this. So it is peaked somewhere here and goes to 0 at 0 meters per second and 4 meters per second initial velocity. And yeah, we can use collocation on that thing. Now I just use 7 points just to save some time. And then this is what we get. So we see interpolation is pretty good here, but it's really bad over here and also really bad close to 0. But that is not so bad, because considering our probability distribution, the probability to get the model into the state is very low out here, also very low close to 0. This is why the interpolation is not good at these points, because we don't need it there. We need a good approximation here where the distribution is high, or more likely. Now, in the end, I just want to say something about high dimensions. Normally, if you go to very high dimensions, these kinds of methods don't work so well, because the number of points you need increases very fast, right? So if we take a full tensor grid, these are the points in the configuration space of some hypothetical model which have to be evaluated. And as the dimension increases, the number of points increases. very rapidly. A solution to that is called the Smolyak sparse grids, which are distributed more like this. And one can show that they also give a reasonably good approximation to the function and the expectation and variance values, while they don't depend very strongly on the dimension of the random space. And this is all already implemented in my package. If you are interested in more functionality, and if I get enough feedback, I may implement many other methods and extensions to this method. Yeah, thank you.
When you drop the terms going to Boltzmann, could you go back to that transparency to look at those terms again?
Yeah, basically.
Right. Yeah.
So they're all very, very large, complicated expressions.
Right. So you've left out the epsilon to the -1s with that spatial operator, is it?
Yes. Yeah. I mean, it's also. I mean, it originally comes from the second order scale.
Right.
So it could be that the thing we are looking for is not a Schrödinger equation, but some other equation which has these terms on the second order. And then they would incorporate there very nicely. But I don't know what kind of equation that is, or how to solve these things. So it needs some time to. I need some time to think about that in more detail.
The delta V part, is it, or delta nu, is it?
Yeah.
Is that then small order, do you think?
So I can plug in numbers and see that delta nu is, I think, of order 10 power -5 compared to this 1 here. Now, of course, I haven't specified epsilon really, right? This is just my scaling parameter, which drops out in the end.
Yes.
And everywhere I assume epsilon is small, but I haven't assumed how small. So it is small compared to 1, but it may or may not work.
Yeah, yeah.
So as I said, this is a serious flaw in the derivation. But it was the only way for me to go forward at this point.
So you would think if you would have essentially a perturbation, it would be represented by that in other like terms.
Yeah, that would be nice.
Mike?
This is sort of a talk of three halves, and I just wanted to, while we're on this topic here, I think that smallness is super important in all that we're doing. We've got to have that idea of smallness, like small scattering, weak scattering, right? We're in some limit where it's not a strong, so it's, and I wonder whether that, this seems really sensible. But, so you taking that limit to smallness and just getting rid of terms is just being prepared to do that sounds a great idea to me. The generalized polynomial calculus is something I just don't get it. Maybe you can help me out here.
Okay.
So I've got some function. It's a clever way of calculating the distribution I get when I randomly vary something that I put into a model of a deterministic model, and I can put in different values for the Young's modulus, and I get out these different values for scattering. And I want to understand how the one distribution affects the other, and without doing a huge amount of sampling. Is that right?
Yes.
Yeah.
That is the idea. So that is the idea of the pseudospectral collocation method, which is a subclass of polynomial chaos methods. So there's another kind called Galerkin methods, but they are intrusive in the way that you have to rewrite all your equations in your model. You cannot just take your model and evaluate it a couple of times. You have to actually change the equations in there and expand your random variables in a random space and use a Galerkin method there. So my package also provides methods to work with that more easily, but the collocation method is generally much easier to implement because you can just take an existing model and do exactly what you just said. Does that answer your question?
Yeah, it does. I mean, I should talk to you afterwards because I've done some strange averaging myself, and I ended up with a distribution that had finite variance but infinite standard deviation, which is quite dangerous to work with, right?
Yeah, that does. No, that does not work.
Yeah.
Okay.
Sorry, finite mean infinite variance. Sorry.
Okay.
Yeah, you're right.
Okay.
Yeah.
Okay.
Sorry.
Good.
Okay, so our time is up. I will ask you my question afterwards.
Okay.
Thank you very
All
much.
right.